Okay, settle down. Let's talk about new things. So what I'd like to talk about today is gravitational force. All right. Now, you've already been to the lab once, right? The physics lab. And did you play around with these nice, almost frictionless rails? So it's really nice. I mean, you can test accelerated motion, motion with constant velocity, all these nice things. The thing is, Newton didn't have one of those. Poor guy, you know. He really did not have any environment where he could test his ideas for things moving in vacuum. Okay. What he had, the only kind of frictional motion he could actually observe was the motion of planets. Okay. Planets around the sun. The problem was that in his day, people thought laws governing motion in our, on the surface of the Earth, and laws governing motion of planets, stars, all other things, were two separate things. There was heaven, there was Earth. So the great idea Newton had was that maybe he's going to write down one law which is going to explain both heaven and Earth. He will make a synthesis of these two different things. He will write down universal laws. And that caused a lot of stir in his day. So there is this guy who's trying to explain the motion of planets writing equations. Now, here's the thing. Newton really started from a simple assumption, simple point. He said, hey, if I have two masses, m1 and m2, and if the distance between them is, let's say, r, both of them experience an attractive force. So they're attracted to each other. Let me call this Fg. The magnitude of this force, Fg, is proportional to both masses and inversely proportional to the square of the distance between them. Okay. And he said there must be a universal constant in front, which we now call Newton's gravitational constant, G. And the great thing about Newton is that once he started out with this force formula, by applying F equals ma, so this gravitational law plus F equals ma, he could really write down equations which explained motion of the planets around the sun to a great degree of accuracy. So that's sort of what made Newton famous. He showed that what was observational laws of Kepler. Kepler said the planets move in ellipses. He said two more things we're going to learn in 2 days. And he could explain all of these laws just from this inverse square force law. And immediately people probably were a little bit dismayed by this equation because it's supposed to be a universal equation. So let's solve an example. Let's calculate the force of attraction between Ayşe, m equals 50 kilograms, and Ali, m equals 70 kilograms, who are standing 1 meter apart. So here is Ali, and here is Ayşe. Okay, they are standing 1 meter apart. Now, what's the force of attraction? Gravitational force. Now, this is going to be G, m1, m2, over r square. And now I have to tell you the value of g. The value of g, it turns out, is in SI units 6.67 10 to minus 11. How about the unit? What should be the unit of g? Just looking at this equation, I can say it has to be Newton meter square divided by kilogram square. But Newton is kilogram meter per second square. So it's meter cube per kilogram second square. Okay? No, I think that's correct, right? So let's put these numbers in. 6.67 10 to minus 11. M1 is 50. M2 is 70. R is 1 meter, so 1 square. All in all, that is 35 times more or less 7 10 to minus 9 newtons. So it's going to be 3.6 10 to minus 10 newtons. What's the weight of Ayşe? Weight of Ayşe is M to G. It's 50 times 10, around 500 newtons. So the attraction force between quite massive objects, 1 meter apart here, is very small. It's almost a billion times smaller than their weight. So this actually, for our daily scales, is a very small force. I mean, is there a force of attraction between my phone and my pen? Yes, there is. But if I actually calculate it, I'll find it to be of the order of 10 to minus 11 or 12 newtons. So you would need extremely precise measurements of force to be able to find out this gravitational attraction. The thing is, gravitational force is generally extremely weak compared to other forces in the universe. For example, in Physics 102, we'll talk about electrostatic attraction, electrostatic repulsion. The electrostatic repulsion between two electrons is 10 to 34 times larger than gravitational attraction. So gravity is a very weak force. However, here is the thing. All the forces you learn about, especially electromagnetism, they come with two flavors. If you have like charges, they repel each other. If you have opposite charges, they attract each other. So those forces can be attractive or repulsive. On the whole, when you have two atoms which are electrically neutral, these electrical forces tend to cancel each other. However, there is no way to cancel a gravitational force. So the more you pile up mass, maybe for individual particles gravity is weak. But when you pile up mass, gravitational force just keeps adding up. So if you have a huge object, like a planet, like planet Earth, then the result of all these small gravitational forces adding up is mg, the force which is actually dictating our life on the surface of the Earth. Yes?
Why is there gravitational force?
Oh, that's such a deep question. Okay, why is there gravitational?
For Earth planets, we can say that in core of Earth there's metals which have magnetic property. That's called, for example, for this plastic, why should be force between this and another?
Okay, so that's that again. I'm saying gravitational force is not in electrical in origin. It's not magnetic in origin. It's really an empirical law that any kind of mass in the universe gives us an attractive force between two objects. Einstein in relativity found out that you can maybe describe this more deeply in terms of bending of space and time. Okay, but that's really a deep question. I don't think there is, in physics, we are not good at answering the question why. We're better at answering the question how. Okay. How come is there an attraction between two massive objects? And I can give you detailed equations on how much this guy bends space-time so that the motion of the other is affected. Okay? Yes?
Light can be affected from gravity.
Yes, yes, but that has no bearing here. So what's the point?
It means that light has a mass.
No, that doesn't mean that. Light doesn't have a mass. Light doesn't, it always moves with light speed, but that's again a question for relativity. Okay? So it gets more complicated. The formula we write down here does not take into account motion when the motion of the object, the velocity of the object is close to the speed of light, or this formula is not valid if there is so much mass at some point that the space-time bending is too large. So it does not apply to things more massive than neutron stars like black holes. But nonetheless, this is a remarkable formula. I mean, in its day, it was like a miracle. Okay, before that, people really thought the motion of the planets was something heavenly. It dictated our lives on Earth. That's why astrology was a big thing. And then Newton wrote a simple-looking equation which predicts the motion of all these dots in space extremely accurately. Okay. Now, here's the thing. I said it's weak, but I must really be careful here. That formula is correct for point masses. So Ali and Ayşe should really be point-wise. Or it's also correct, and we'll see why it's correct in physics 102, if they are actually spherical. So there are spherical approximations to Ali and Ayşe. Okay? That's a joke. You're supposed to laugh at my jokes. Okay? So now, here, F is G m1 m2 over r square, we said. And here's the thing. Why don't we observe this 1 over r square behavior? I mean, I said I'm on the surface of the Earth. So let's say this is our Earth's surface. And this relation is correct for spherical distributions. So I can think of Earth as if it's just a point mass at its center. All right. And here I have an object, a height h above Earth. How come I said this just is attracted to Earth by a constant force mg? Right? And that's, I'm saying these two formulas are actually, they have the same origin. Here's the thing. Motion on Earth's surface. So on Earth's surface, what do I mean by Earth's surface? What's the typical value of h I would use? A few meters, maybe. I mean, so far that's what I said. Let's take h to be 10, maybe 100, maybe 1,000 meters. Okay? So what's really the gravitational force between an object at height h and Earth? F gravitational must be g m Earth times m divided by, here's the thing, right? It's the distance between two objects, but I'm thinking of the spherical Earth as if it's a point mass at its center. So the full distance here is going to be r Earth plus h squared. What is our Earth though? Can anyone tell me the value of Earth's radius? Yes.
6,400 kilometers.
Okay, so approximately I would say it is 6,400 or 6,300. Let's say just 6,000 kilometers. Okay. So how about H and RE? What's the ratio here? So let's say I take H to be 1,000 meters. In the worst case, I'm throwing something from a mountain. This is 1,000 meters divided by 6,000 kilometers. So this is a number of 10 to minus 4, almost 1 over 10,000 order, right? So it's a very small number. Now, here is the thing. Let's make some approximations. If I have, for small values of x, let's say I have a very small number, 1 plus x to the n. So if x is much less than 1, what is 1 plus x to the n? Now, please follow me. Please stop writing. This is an important approximation. We're going to use this over and over again. Now, I know the binomial expansion. So the first term will be 1. The second term will be n times 1 to the n minus 1 times x. The second term will be n choose 2, 1 to n minus 2 x squared. Now, if a number is much less than 1, which is more important, x squared or x? Let's say, let's just put x equals 0.01. If x is 0.01, the number here will be 0.01. X squared would be 0.001. So higher powers will be smaller and smaller. Right. So here's what I can do. I can actually just neglect the higher powers. And I can say for small values of x, 1 plus x to the n is almost 1 plus nx. You don't believe me, but you'll believe my computer. So here's what I'll do. I'll take x to be 0.0003. Okay. And I'd like to calculate 1 plus x squared. So 1.00003 square. Did I have the correct number of zeros? No. And I'm saying that this should be really 1 plus 2x. This should be 1 plus 0.006. Let's check. Let me open my calculator. Hopefully it's somewhere over here. So 1.0003. I'm going to take its square. Okay. So you see, you even see the next order contribution here, but it's really, really small. Okay. So I could say this is a pretty good. Oops. I think I opened up Python. Okay. So you won't need it now. So you see, this is a good approximation. Okay. Try to do it for other powers. So Do you believe me? Is it more believable right now when the computer actually tells you the correct numbers? Good. So here's what I'll do. The gravitational force is G m Earth m divided by r Earth plus h squared. I will say this is, hey, G times me times m divided by r Earth square 1 plus h over re squared. I can always do that. And then I will say this, well, here, this is just an equality. Here is my approximation. I'll say 1 plus h over re square is actually G m Earth m over r Earth squared times 1 minus 2h over re. So gravitational force is apparently G me over re squared times m. And the first correction is apparently G me over r Earth squared times 2h over re. There are higher terms which we neglect. So what is the first term? It's exactly what we use, mg. Okay? So what we call G, gravitational acceleration, is actually Newton's gravitational constant times m Earth divided by r Earth squared. So how about the second term? It tells me essentially that G gets smaller and smaller as I move away from the Earth. Okay? But it doesn't really get that small because h, even if you go to Mount Everest, which is 8,000 kilometers up, 8,000 meters up, it's not even 1/10 of Earth's radius. It's 1,000th of Earth's radius, right? So this correction will be very, very small. It will be of order of 1,000th of g. Okay. So what does that tell me? If I know g, I know something about Earth's mass. This is essentially, whenever I'm actually weighing myself on a balance, I'm not only weighing myself, I'm also weighing the Earth. Okay, I'm actually looking at the force between Earth and myself. If I know my mass very precisely, I can also know Earth's mass very precisely. Well, that's not entirely true because Earth actually is not a perfect sphere. Okay, it's a little bit compressed at the poles. Okay. Furthermore, it's also rotating. Right. So here's an other question. Find how fast the Earth would need to rotate so that the masses on the equator feel weightless. So if I'm making the Earth turn faster and faster, if it goes very fast, at some point, if I'm on the equator, I'll just feel weightless. Let's try to find out. So let's take the Earth to be a perfect sphere. with radius RE and mass ME. So if I'm standing on the North Pole, what's my free body diagram? Standing on the North Pole, my free body diagram is that I will have this mg down. And why do I not sink onto the Earth's surface? Because Earth's surface is applying a normal force and to me. If I'm sitting on a balance, what would the balance weigh? It will exactly weigh this normal force. It will measure that normal force, right? That will be my weight. Now let's assume that Earth is rotating with some angular frequency omega. Okay? Angular frequency omega. So if I'm exactly on the equator, what is my acceleration? So I'm essentially going around the circle here, right? With radius RE. So my acceleration is towards the center. Right? And that acceleration will be v square over r Earth. But v is omega times r Earth. So it's going to be omega square times r Earth. So if I am on the equator, what are the forces on me? I will have mg pulling me towards the Earth. I'll have the normal force on and pushing me outward. But there is an acceleration a towards the center. Why? Because the Earth is rotating. So let's find out what does feeling weightless mean? It means if I step on a balance, it will show 0, right? So there is no normal force. Question? Comment? You sure? Read. Okay, that's fine. You could ask also that. Probably other people cannot read my handwriting too, so that will help. Now, what do I want for weightlessness? N should be 0, which means ma should be equal to mg, or in other words, omega square r Earth must be equal to g. So from here, I would find omega to be g over r Earth square root. Okay. So let's try to find out what this omega comes out to be. First of all, what is the omega of the Earth? Okay, let's first calculate. Let's put in numbers. G is more or less 10 meters per second square. R Earth, I said, is 10 to 6 meters. So let's put in the numbers. That's going to give me 10 to the 5. Right? So let me pull up my calculator again. So it's going to be 1 over 6, 10 to minus 5, right? Where's my calculator? Oops, I'll have to open it again, I guess. So I basically want to divide 10 divided by 6 is 1.67, 10 to minus 6. So it's going to be 10 to minus 3 square root of 1.67. So let's find the square root of that. Do I keep closing my calculator? Okay. Square root of that is 1.3 10 to 3, 1 over seconds. How fast of a rotation is that? It's not a very fast rotation, you might think, right? That's a small angular velocity, 10 to minus 3. What's current omega? Still, let me do it in a other way. What's the current omega of the Earth? What is the period of Earth's motion? 2 pi over omega. Earth rotates around itself in 1 day, right? So it should be 1 day. 1 day is 24 hours times 60 seconds times 60 minutes seconds. So let's do that. Omega current is, where's my calculator? Okay, let's clear everything. 2 times pi divided by 24 hours divided by 60 minutes divided by 60 seconds. So 7.27 e to minus 5. So if I compare these two things, if the Earth was rotating, I would say 15 times faster, then things at the equator would be actually flinging outward. They would feel weightless. So it's not, you may think it's really not that fast. At least I was surprised. So if 1 day of the Earth was almost 1 hour, people at the equator would feel almost weightless. Now, there's a very good reason why that doesn't happen. Because if your object, and all these gravitational objects, most of the planets, stars, they cool from some sort of liquid into a solid if they cool. So if they were rotating too fast, so that whatever is at the equator is going out, that piece would have broken off and formed either a ring or a satellite around the object. So that's why you would never actually see this limit. Unless you actually have an asteroid which starts rotating faster because something hits it after it has cooled. Okay? Question?
This means that our Earth's angular velocity is. I'm saying that the acceleration comes from angular velocity should be added to g.
Yes. So you're
2.5%.
So what you're basically saying is that even with this angular rotation, the g at equator and g at the pole must be different. Yes, they are different. But it also turns out that Earth is not a perfect sphere. Okay? That effect balances out part of this effect, but still g varies a lot on Earth's surface. Why would it vary? I mean, we have talked about this. People are trying to measure g very, very accurately. Why? Because not only does it depend on Earth's rotation and Earth's radius, but locally Earth is not uniform. Under certain regions, there are high density things like mines, right, where heavier metals actually form. Or there may be big caves or big regions with small density below you. So local G is determined by a lot of other factors, local factors. People actually use that to their advantage to see if there is natural gas or oil or other less dense objects below Earth. Okay? Now, let's talk about one more thing. You've always seen, let's say International Space Station. Inside the International Space Station, you look in and you see these astronauts are flying weightlessly, right? Why are they weightless? Why do they? Well, always the answer is that because they are in space, right? Do you know how high up are they from Earth's surface? What's the?
400 kilometers.
Yes, excellent. So it's exactly, so Earth, the ISS is orbiting 400 kilometers above Earth. So is the gravitational pull of Earth on the astronauts small? Let's try to find out. Here is my Earth. And our Earth is 6,000 kilometers. Well, let me be more clear. I think it's actually 4,380 kilometers. Okay? How about the International Space Station? It's just 400 kilometers. If I try to be on scale here, so here is my International Space Station. So this is 400 kilometers. So what's the gravitational G at ISS? I mean, maybe it's not, G is not equal to 9.82, but it's certainly somewhere around 9.5 meters per second square. So they are not that far apart. How come do the astronauts feel no weight inside the station? Well, here's an easy way to feel weightless. Let's go to Dubai. Get on an elevator in the Burj Khalifa, the highest building on Earth, right? So we are here on an elevator in Burj Khalifa. Let's go to the top floor and ask a friend to cut the elevator, the cable. So what will happen? Here's what will happen. The elevator obviously will feel its mg. There is no friction force, there is no cable. So this thing is accelerating down with g. And here you are. You also feel your, so this is m elevator. This is your mass, m, g, which means you're also accelerating with g. With respect to the elevator, you have no acceleration. So you're very happy you don't even float like this. You're very happily floating, right? You're weightless until, the moment of crash, of course, right? And it's not going to take very long. However, the important thing is if you're both accelerating, if you're both the elevator and yourself are in free fall, you do not experience weight with respect to this environment. So here is something nice which was taught by Newton. And this guy was really a genius, right? So he said, let's go to some mountaintop and put a cannon there. if I fire the cannon, the cannonball will hit the Earth somewhere further. But if I actually hit it, if I fire it more velocity, what it will do is it will fall, but it will actually fall further because Earth is curving. Right? If I give it more velocity, it will fall even faster. It will go even longer because Earth is curved down so much. So there must be some critical velocity. If I actually fire with that, the cannon is falling towards Earth with g, but Earth is bending with the same radius, with the same curvature, so that this cannon actually, the cannonball makes a full circle without falling down. And this is exactly what the International Space Station is doing. People in that are falling. The whole thing, the International Space Station is falling. However, they are going so fast that as they fall, the Earth curves behind them, below them, right? So their distance from the Earth is conserved. So I find it, somehow, I find that idea of satellites and space stations very disturbing. That thing is falling. It's in free fall. Okay. And you think you're very happy. Hey, I'm in weightless. You know, actually, you're also falling towards the Earth. Thank God you're going so fast that Earth is curving. It's just Earth is getting out of your weight. All right. So let's try to find out what should be the speed so that you're actually not falling to the Earth. Well, so to be around the orbit in a planet, if that's the mass of the planet, if that's the full radius, which is going to be your height plus radius of the planet, how fast do you need to go so that you're in a stable orbit? How are we going to solve this? We're going to plot the Freebody diagram. Here are the forces acting on my space station. It's just going to be gravitational force. There is no other force acting on my space station. But it also has an acceleration. Acceleration is towards the center, and its value is going to be v squared divided by the full r. So m times a must be F gravitation. M times v squared over r must be g m planet m divided by r square. M's cancel nicely. V must be g times m planet divided by r square root. Or if you want, we said g m Earth over r Earth square is g, right? So this you could also write as g approximately g times r Earth, or whatever radius you're looking at. So what are the typical speeds of satellites and space stations if they are not very far apart, very far away from Earth's surface, so-called low orbit satellites? Well, g is around 10 meters per second square. Our Earth is 10 to 6 meters. So this whole thing is almost 10 to 8 meters square per second square. So it's 10 to 4 meters per second. So typical orbital speeds are 10 kilometers per second. So why do we need all these big rockets to put something small like a satellite into the Earth orbit. It's not that we actually have to go up the atmosphere. It's that we have to give all this velocity. 10 kilometers per second is a very fast velocity. The only thing which reach 10 kilometers per second in the atmosphere are rockets and, God forbid, meteorites or meteors. Okay, so that's a huge velocity. So we need these huge rockets not to go very high up, but rather to go into orbit, which requires a lot of lateral speed. Okay, good. So one more example. This low orbit is good for International Space Station. It gets to travel all around the Earth. It takes nice pictures, right? But it's not useful if you want to have a communication satellite. Okay, so you want to get some satellite reception. Let's say you paid, I don't know, 100 liras per month to watch Turkish Football League games. What happens if the satellite is actually moving with respect to Earth? Then you'll have to have a intelligent satellite dish which will track the satellite, which is not good. So if you want a TV satellite that's going to beam you TV, what you want is, with respect to Earth's surface, it should remain stationary. So let's find out. Such orbits are called geostationary. Let's try to find out where those satellites are. Question.
There are also geosynchronous orbits.
They are the same thing.
Yeah, synchronicity, they should fall towards the Earth, and they,
No. Okay, that's a good thing. Geostationary means it's stationary with respect to Earth. What does that mean? Earth is rotating in 24 hours. What we want is that this satellite is also rotating in 24 hours. So when you actually track it once, it never changes. Both you are rotating and the satellite is rotating. No. Let's solve the example. I don't know why you think it should fall down, but here's the thing. Here is my Earth, and I'm looking at it from the North Pole. Here is my geostationary orbit, RG. So what do I want? Here is V, and I'll again write the same thing. The acceleration of this object would be v square over rg, and that would be equal to g m Earth over rg square times m. M's cancel. V is square root of g m Earth over rg. What do I want this v to be? I don't want v to be something, but rather what I want is the period to be. So the whole time, the time it actually takes for this object to go through one orbit to be 24 hours, which is going to be 2 pi rg divided by this velocity. So if I write everything, this is going to be 24 times 60 times 60 is going to be 2 pi, and putting everything here, I have rg divided by square root of g m Earth rg. So this is going to be 2 pi 1 over square root of g m Earth times rg to the 3 halves I don't have time to do the algebra. Find out where this geostationary, how far away this geostationary orbit. You'll see that it's almost another Earth radius away. So it's actually quite far away. And those orbits are very expensive. To put a satellite into that orbit is actually more expensive than putting something into low Earth orbit. I'll see you in 2 days, 3 days.